Welcome to the Deep Dive. Today we're cracking open something you use constantly, probably without a second thought. Flash memory.
Right, it's everywhere.
And it's got a genuinely surprising backstory. Picture this. The mid-1980s, a semiconductor slump is hitting hard.
Yeah, tough times for the industry back then.
And the king of rewritable non-volatile memory, the EEPROM, that's erasable, programmable, read-only memory, it's facing serious price pressure.
Good time. Lots of competition.
And you, the customer, you're kind of over the whole ultraviolet light show, needed to reprogram it.
Definitely not convenient.
The newer EEPROM tech with its electrical erasure looks tempting, but the cost, ouch.
Way too high for most applications back then.
This creates a real hunger, what our sources call a holy grail. Single transistor electrically erasable memory.
Exactly. What's fascinating right from the start is this collision of what the market wants and what technology can actually deliver. You have this very clear demand from both consumers and the industry bumping up against the limitations of what was available.
So this holy grail wasn't just some abstract idea.
Not at all. It was a direct reaction to some very concrete problems people were having with existing tech.
Exactly. And that's where our deep dive begins. For you, the listener, this isn't just some dusty piece of tech history.
Well, way.
This is the foundation of the tech humming away in your phone, your laptop, your digital camera, all those gadgets you rely on every single day.
Totally.
We've gone through a really comprehensive guide for this, non-volatile memory technologies with emphasis on flash.
It's a hefty one. Very thorough.
It's this ambitious attempt to be the definitive reference written by the people who were actually in the labs and the factories.
Yeah, the practitioners doing the groundbreaking research, development, manufacturing.
So think of this as your fast track to understanding the core of what makes your digital world go.
And if we zoom out a bit, understanding where flash memory came from gives you a much better appreciation for just how widespread its impact has been.
Right.
It wasn't a guaranteed success. It was really forged in response to specific needs and evolved through a series of challenges and some pretty ingenious innovations.
Absolutely. So our mission today is to pull out the most valuable insights from this guide.
Distill it down.
We want to give you a solid grasp of what flash memory is at a high level, how it fundamentally works, and why it made the journey from this holy grail idea to the everywhere technology we know today.
Sounds good. Let's jump in.
Okay, let's unpack this. What were the main obstacles in the market that actually led to the invention of flash memory?
Well, the source material really emphasizes two key market forces. First off, the existing dominant player, EEPROM, was facing a lot of price competition.
It's too many players.
Yeah, the market was maturing, over 20 companies all vying for a slice of the pie.
Wow.
Second, and maybe more important from a user's perspective, EEPROM needed that UV light to erase it before reprogramming.
Which was slow and annoying.
Right. People really wanted the electrical erase capability that the newer EEPROM tech offered, but they wanted it at a price much closer to EEPROM's.
So it was this desire for the best of both worlds, really. User-friendliness of EEPROM without the hefty price tag.
That's it. That really set the stage for something new.
And then Toshiba, in 1985, announces this single-transistor electrically erasable memory. And they even came up with this great name, Flash, because it erased so quickly in a flash.
Great name. Stuck immediately.
But here's where it gets really interesting, doesn't it? It wasn't an overnight sensation.
That's such a crucial point. While Toshiba was first with the concept and the name, their initial product was described as being, well, difficult to use.
Oh, really?
Yeah. Because of this, it unfortunately didn't really take off in the market. CQ followed a year later with another flash device.
And
It also struggled to gain traction. Too complex again. These early stumbles really highlight that just having a brand new technology isn't enough. It has to be user-friendly and fit a clear market need.
that's a lesson that goes way beyond just flash memory, wouldn't you say?
Oh, absolutely. A great reminder that even revolutionary ideas can trip on their way out of the gate.
Now, Intel, another major player in this early story, took a bit of a different path initially.
They did.
They tried to develop their own single-transistor EEPROM by partnering with Seqor, who were early pioneers in EEPROM tech. How did that turn out?
Well, the collaboration looked promising on paper, but ultimately it didn't produce a viable product.
Why not? What was the issue?
The fundamental problem was the cell operating window. Think of it like the Goldilocks zone of voltage and current, where the memory cell could be reliably programmed and read. It basically didn't exist. It was either too hard to program reliably or unreliable to read accurately.
Not good.
Nope. This core technical hurdle led to the partnership dissolving. It really underscores just how challenging that holy grail was to achieve. It wasn't just a matter of tweaking existing designs.
So that single transistor EEPROM route kind of hit a wall?
Pretty much.
Yeah. But luckily for Intel, they had this other project quietly going on internally, almost in secret.
The Skunkworks project.
Right, focused on EEPROM-based flash memory. And by 1985, they had a working 64-kilobit chip in the lab. That sounds like a real breakthrough moment.
It was definitely a significant technical achievement, yes. However, what's surprising is how it was initially received within Intel itself.
How so?
According to our source, the Intel EEPROM business unit was actually not very enthusiastic about commercializing this new flash memory.
Really? Why not? They had a working chip.
Well, part of their reasoning was based on Toshiba's initial struggles in the market, made them doubt if customers would actually adopt it.
Okay, understandable maybe.
But perhaps even more significant was the fear that flash memory would eat into Intel's existing and very profitable EEPROM business.
The innovator's dilemma. Cannibalization fears.
It's a classic case of a successful business being hesitant to disrupt itself.
Talk about a huge opportunity almost being missed. It's incredible to think that this technology, which is so fundamental now, almost got sidelined by internal politics.
It really is.
So who stepped in? Who saved it?
This is where the leadership of Gordon Moore, Intel's co-founder, and a dedicated group of individuals really made a difference.
Moore's Law himself?
The very same. Recognizing the immense potential despite the skepticism, Moore intervened. And in 1986, Intel made the crucial decision to form a separate flash business unit.
Smart move. Give it space to grow.
Exactly. This dedicated focus allowed flash memory to develop and mature within Intel, independent of the concerns of the EEPROM division.
So the insight here isn't just about smart leadership, but how crucial it is to nurture disruptive innovation.
Absolutely. Even when it potentially challenges your current successful businesses, that's still incredibly relevant today, wouldn't you agree?
Couldn't agree more. And just 2 years later, in 1988, Intel introduced a 256-kilobit flash memory.
They moved pretty fast once the unit was formed.
What was their strategy for actually making this a success, especially after seeing Toshiba's early difficulties?
Intel's strategy was actually quite smart and very practical. They designed their 256-kilobit flash memory to be a direct replacement for existing EEPROMs.
Drop-in replacement.
Crucially, yes. It had the exact same package pinout, the way it physically connected, and the same control signals as EEPROM devices.
So customers didn't need to redesign their whole system.
Exactly. They could essentially just drop it into systems already designed for EEPROMs without significant costly redesigns.
Makes sense.
Plus, over 95% of its manufacturing steps were identical to EEPROMs.
So they could use their existing factories.
They could leverage their existing EEPROM fabs to quickly ramp up production volume. This focus on backwards compatibility and using existing infrastructure was absolutely key.
Lowered the barrier to adoption significantly.
Hugely. Made it much easier for people to switch.
Okay, that makes perfect sense. So we know flash memory is non-volatile, meaning it keeps its data even when the power is off. But how? How does it actually achieve that?
Right, the fundamental mechanism.
Yeah.
The secret lies in a special type of transistor called a floating gate transistor.
Okay. Floating gate.
Imagine a standard field effect transistor, but with an extra conductive layer, the floating gate nestled inside the insulating layer.
So it's insulated all around.
Completely surrounded by insulating material, yeah. When we want to store data, we essentially trap an electrical charge on this floating gate.
And because it's insulated.
The charge has nowhere to go. It remains there even when you turn off the power.
Oh, okay. And how does that store a 0 or 1?
The presence or absence of that charge changes how the transistor behaves, whether it conducts electricity or not, when you apply a certain read voltage.
So the charge acts like a switch state.
Pretty much. This difference in conductivity is what we interpret as a 0 or a 1, are fundamental bits of digital info.
So it's like a tiny digital time capsule holding on to that charge.
That's a great analogy.
Yeah.
Makes you think about all the tiny time capsules inside your phone right now, doesn't it?
It really does. So that's the basic building block. But how are these cells organized into something usable? What's the overall architecture of a flash chip?
Okay, at a functional level, a flash memory chip has several key components working together. At its heart is the memory array itself, a vast grid of these floating gate transistors.
The grid of time capsules.
Yeah. To access specific locations in this grid, we have row and column decoders. They act like address locators.
Like street and house number.
Exactly. Then there are the read and write circuits, responsible for sensing the state of the cells charged or not, and for altering the charge when we write new data.
Okay.
You also have address and control buffers to manage the incoming signals, telling the chip where to read or write and what to do.
Makes sense.
And finally, there's a control and power management unit overseeing everything, including generating the necessary voltage levels.
And it manages itself internally.
To a large extent, yes. Many internal operations, like the automated sequences for reading and writing, are managed by on-chip state machines, essentially mini controllers within the chip itself.
It sounds like a surprisingly complex little city working behind the scenes.
It really is, just to store all those photos and apps on your phone.
Now, we've seen how the initial need sparked its invention, but what really propelled flash memory into the mainstream made it so incredibly widespread.
The source material makes a really strong case that the explosion of mobile electronics was the perfect storm.
Ah, the rise of cell phones, MP3 player.
Exactly. Cell phones, handheld computers, digital music players. These devices had very specific needs. Small, lightweight, power-efficient, rugged.
And they needed storage, obviously.
Right. For both the software to run them and ever-increasing amounts of user data, flash memory checked all those boxes.
How so?
It offered low power consumption, non-volatility, it was relatively fast, and the chips themselves could be made quite small.
Compared to what? Hard drives.
Yeah, the alternative storage options back then, like traditional hard disk drives, just couldn't meet the miniaturization and ruggedness requirements of these portable devices.
That low power and small size aspect really highlights why your phone doesn't have a tiny hard drive spinning away inside it.
Absolutely. Imagine the battery life.
And as these mobile devices got smaller and sleeker, that must have put pressure on the chip packaging too, right?
Oh, huge pressure. The constant demand from OEMs, the companies making the gadgets for smaller, lighter, thinner products, directly translated into demand for smaller, lighter, thinner memory chips.
So how did the packaging evolve?
In the early days, you had DIP packages dual in line with pins you stick through the board,
The classic look.
and PLCC packages, plastic leaded chip carriers, which were early surface mount.
Surface mount being key for smaller designs.
Definitely. The chip sits right on the surface, allowing much denser boards. Over time, these gave way to even smaller surface mount packages like SOP, small outline packages. And more recently, BGA packages ball grid array, tiny solder balls on the underside.
Right, you don't even see pins anymore.
Exactly. This evolution in packaging has been absolutely crucial for the miniaturization we've seen.
So smaller chips and smaller packages were key. Now, as we delve deeper, we encounter this really important distinction. NOR versus NAND flash.
Ah, yes, a fundamental fork in the road.
It sounds like it. What's the core difference between them, and why did these two distinct types emerge?
This is really critical.
Yeah.
While both NOR and NAND use floating gate transistors, they have fundamentally different internal architectures.
And that means they're good at different things.
Precisely. They excel in very different applications. NOR-type flash is designed for fast, random access.
Meaning?
Think of it like being able to instantly jump to any page in a book. The CPU can quickly access any memory location, even if they aren't next to each other.
So good for running code.
Ideally suited for storing code, yeah, where the processor needs instructions quickly and reliably. It also boasts high reliability, long data retention, 10+ years often,
Yeah.
and typically doesn't need complex error correction.
Okay, NOR is for code execution. What about NAND?
NAND-type flash prioritizes high storage density and low cost per bit.
Storing lots of stuff cheaply.
You got it, like being able to store a huge library in a small space.
Yeah.
However, it has significantly slower random access times.
How much slower?
We're talking microseconds compared to nanoseconds for NOR. Big difference.
Oh.
Also, NAND flash is more prone to occasional bit errors, so it usually requires sophisticated error detection and correction ECC to ensure data integrity.
So summarizing, NOR is fast, reliable, good for code.
Yep. Think of NOR as running the show.
And NAND is dense, cheaper, good for data storage, like photos, videos.
Exactly. NAND is the cost-effective workhorse for storing vast amounts of data.
That clears it up nicely. NOR for running the show, NAND for storing all this stuff. Now, you mentioned access times for NOR, 55 to 150 nanoseconds. That sounds slow for modern CPUs.
Well, those were early figures. And you're right, CPUs got much faster. Traditional flash used an asynchronous interface, like older memory, send an address, wait for data.
Which could cause the CPU to wait.
Exactly, introduce wait states. But modern systems use more advanced read interfaces like page mode and burst mode.
How do those help?
Page mode allows much faster sequential access within a specific block or page. Burst mode lets you transfer a continuous block of data at high speed once you have the starting address.
So better for grabbing chunks of data quickly.
Significantly, these techniques reduce latency and let high-performance CPUs fetch data much more efficiently, often avoiding those wait states.
That makes sense. Keep the data flowing smoothly. Now, shifting gears a bit, flash memory isn't just embedded directly. We also have removable flash cards.
Right, for cameras, phones, etc.
What are some common formats and how do they fit in?
Flash memory cards provide a really convenient way to extend storage and transfer data. We've seen various formats: older PCM CIA cards, compact flash, the ubiquitous SD cards, smart media.
Quite a few.
Yeah, the source mentions those. A common design is inserting them lengthwise into a slot.
And can you use different types easily?
What's quite useful is the data interchangeability. Adapters are readily available. You can read a compact flash card in a PCM CIA slot or read older cards via USB adapters.
Ah, so adapters bridge the gap.
Exactly. This interoperability has been a significant benefit for users, accessing data across devices, even with different card formats.
So despite the different shapes, adapters provide some universality. Now let's talk about code plus data convergence. Sounds like Flash evolved beyond just running programs.
It really did, a significant step forward. Initially, Flash was mainly seen as an EEPROM replacement for code, letting you update software in system.
The key advantage back then.
Right. But the long-term vision was always a more unified memory solution, storing both program instructions and user data, your documents, media, all on the same chip.
But that must have required changes.
Oh, yes. To make that reality, several key advancements in architecture and technology were needed to handle these two different types of information efficiently on one chip.
Not just one single breakthrough?
No, our source emphasizes it was a combination of different features building on each other.
Okay, so what were some of these key enabling features for handling both code and data effectively?
One crucial set revolves around managing read and write operations more flexibly. Capabilities like write suspends and dual partition.
Write suspend? What's that?
In a standard single partition flash, if you're programming or erasing data, you can temporarily pause that operation to allow a read to happen elsewhere in the memory.
Why is that important?
Vital in code plus data systems. The main program code might need to execute, say, to handle an interrupt, a sudden request, even while the program writes is ongoing elsewhere.
Got it. And dual partition.
Takes it further. Allows simultaneous read and write operations in completely separate, isolated sections or partitions of the memory.
Like having separate work areas.
Pretty much. The choice between single or multi-partition often boils down to system performance needs. How much throughput do you need for both storing data and running code?
So if demands are high, multi-partition avoids bottlenecks.
Exactly. Like having separate lanes on a highway for different traffic types, preventing congestion.
Makes perfect sense. What's another key piece? Our outline mentions software media management.
Yes, software plays a truly critical role here. Flash memory, unlike RAM, erases data in relatively large blocks or sectors.
How large?
Can range from 8 kilobytes up to 128 kilobytes, or even more. Significantly larger than many individual pieces of data you might want to update.
And you can't just erase one byte.
Nope. So it would be incredibly inefficient to erase an entire 128 kBp block every time you wanted to update, say, a small configuration setting.
Okay, so how does software help?
This is where sophisticated software media management comes in. Algorithms cleverly manage these large blocks. They might store and update multiple smaller pieces of data within one block.
And when data needs updating.
The software might find empty space in the same block or move data around between blocks to avoid erasing the whole block unnecessarily.
Minimizing those slow erase operations.
Dramatically reduces erase cycles, which is really important for extending the overall lifespan and reliability of the memory.
So the software acts like a very smart librarian, optimizing how the blocks are used.
That's a good way to put it. Keeping track and minimizing wear.
Now let's talk power. We mentioned Flash needs to be power efficient for mobile devices, but programming and erasing need higher voltages, right?
They do, yes. Typically higher voltages than just reading data.
So how are those generated on the chip itself? It can't rely on the main device battery providing 10 volts, surely.
No, definitely not. These higher voltages are usually generated internally using specialized analog circuit blocks. These include charge pumps and voltage regulators.
Charge pumps, like tiny voltage boosters.
Essentially, yes. They take a lower input voltage and through rapidly switching capacitors, effectively pump it up to a higher level.
And regulators.
They step in to ensure these generated voltages remain stable and within the precise range needed for reliable programming and erasure.
Seems quite sophisticated.
It is. Our source even mentions that during chip development, these analog blocks often have test points, allowing engineers to monitor internal voltages and signals for debugging.
So it's like having a tiny, highly controlled power plant right there on the memory chip.
Pretty much sums it up.
Now, manufacturing these incredibly dense chips must be challenging. Defects must happen. How does the tech address this to get a reasonable yield?
That's a constant challenge. One common and effective technique is called column redundancy.
Redundancy, like backups.
Sort of. The basic idea is to add one or more extra spare columns of memory cells to each sector or block of the array.
Okay.
If, during testing after manufacturing, a regular column is found to be faulty.
You swap in the spare.
Exactly. A redundant column can be activated to take its place. It involves extra circuitry, like multiplexers acting as electronic switches, to redirect connections from the faulty column to the working spare.
Like having a spare tire on your car.
That's a great analogy. This built-in fault tolerance is crucial for achieving acceptable manufacturing yields, especially as densities increase and cells shrink.
Makes sense, like having spare lanes on the memory highway. Now, pushing for even higher densities, storing more than 1 bit per cell, multi-level cell, MLC.
Oh yes, MLC, a key enabler for cost reduction.
How does that work and what new challenges does it bring?
Moving to MLC is a key way to significantly increase storage capacity without making the chip physically larger or the cells smaller.
So instead of just 0 or 1.
Instead of traditional single-level cell, SLC, storing 1 bit, MLC allows a single cell to store multiple bits by using more than 2 distinct levels of charge on the floating gate.
How many levels?
For 2 bits per cell, you need 4 distinct charge levels. For 4 bits per cell, you'd need 16 different precisely controlled charge levels.
16 levels in one tiny cell. That sounds difficult.
It is. The fundamental challenge is that as you increase bits per cell, the voltage differences between adjacent levels become much, much smaller.
Tighter margins.
Extremely tight. In SLC, the difference might be a few volts. In a 4 bits per cell MLC, the voltage margin to reliably distinguish between states can shrink down to maybe 0.15 volts.
Wow, that's tiny. Very sensitive to errors.
Much more susceptible, yes. Especially to errors from slight charge leakage over time data retention degradation.
So how do you make that reliable?
This is where sophisticated error correction coding, ECC, becomes absolutely essential. ECC circuitry detects and corrects these potential bit errors, ensuring data integrity.
So you gain density but add complexity and need strong error correction.
Exactly. It highlights a fundamental engineering trade-off. You gain density, but introduce complexities in managing fine charge levels and error correction.
So more storage, tighter margins, need for ECC. Now, given all this intricacy, how do they even test these chips thoroughly?
Testing flash memory presents some very unique challenges. First, you need good chip observability, being able to see the internal workings to verify function.
Okay.
Second, program and erase operations involve multiple steps, high voltages, and take noticeable time. So reducing test time is crucial for cost.
Keep manufacturing efficient.
Right. And finally, chip configurability, ensuring it can be accurately set up for its intended use.
And the high voltages complicate things.
They do. Even as logic voltages drop, program arrays voltages remain high, maybe 10 volts or more. This difference complicates testing.
How?
You need careful monitoring and adjustment during test. Plus, operations involve long voltage pulses, maybe repeated many times, adding to test time.
So what techniques do they use? Design for testability.
Yes, DFT techniques are key. They might build special test modes into the chip.
Activated how?
Using specific, unusual signal combinations or even temporarily applying voltages slightly outside the normal operating range.
But you wouldn't want users accidentally triggering that.
Absolutely not. So the entry methods are deliberately unusual, maybe sequences that never occur in normal use, or special fuses.
Sounds like a delicate, time-sensitive process to test these complex devices properly.
It really is.
Yeah.
Very carefully managed.
Now, we've mentioned the algorithms controlling programming and erasing. Can you shed more light on how those are managed inside the chip?
Sure. Erase and program aren't simple instant events. They involve carefully timed, precisely controlled steps managed by complex algorithms.
Run by what?
Dedicated algorithm controllers within the flash chip. What's interesting is these algorithms can often be adaptive.
Meaning they adjust on the fly?
Yeah, the next step might only begin once certain conditions from the previous step are met, allows more efficient and reliable operation, adjusting to individual cell characteristics.
Clever. And you mentioned suspend resume earlier.
Right. Flash often supports suspending an ongoing erase program in one area to allow a read elsewhere, vital for systems needing access while other operations are busy.
And the controller manages that juggling act.
The algorithm controller manages suspend and resume correctly, ensuring the interrupted operation can be reliably picked up later.
How does the main system know what the flash chip is doing?
Through a status register. It's implemented within the flash chip.
Like a little status report.
Exactly. It provides info. Is it busy erasing or programming? Did it hit an error? Is it done? The host controller checks this register to monitor progress.
So, a mini processor managing memory ops and reporting back. Now, let's get fundamental. How is data actually written, programmed, and erased? Are they just reverse processes?
Good question. No, programming and erasure are distinct operations, often relying on different physical mechanisms.
Okay.
Also, remember, Flash usually erases in larger block sectors, not byte by byte like EEPROM. And programming is generally faster than erasing.
Makes sense. Erasing a whole block takes time.
Right. Now, the physics of moving electrons to and from the floating gate. There are two primary mechanisms at the atomic level.
Okay, what are they?
The first is Fowler-Nordheim tunneling, FN tunneling.
Tunneling, like through a wall.
It's a quantum mechanical phenomena. Electrons can tunnel directly through a thin insulating barrier, like the gate oxide, even without enough classical energy to overcome it.
Wow. Like ghostly electrons.
Sort of. The probability depends strongly on the electric field strength across the oxide. Higher field, more tunneling.
And this is used for?
Often used for both programming and erasure in some flash types, when a high field is applied.
So it's not brute force, but a quantum trick using electric fields.
Kind of, yeah. A subtle quantum effect making electrons move across the insulator.
Okay, that's FN tunneling. What's the second main mechanism?
The second is channel hot electron injection, or CHEI.
Hot electrons.
Yeah. This happens when you apply a high voltage to the drain terminal, creating a strong electric field in the channel where current flows.
Okay.
This field accelerates electrons, heating them up to high energy levels. Some of these hot electrons gain enough energy to overcome the oxide barrier and get injected onto the floating gate.
So they jump over the barrier?
Effectively, yes. If the field across the oxide also favors injection, they get trapped on the floating gate, changing the transistor's threshold voltage. That's programming as zero.
When does CHEI usually happen?
Typically when the gate voltage is roughly equal to the drain voltage.
Is it efficient?
Generally less efficient than other methods like source-side injection, SSI, mentioned in the source. It tends to inject fewer electrons and consume more power.
So CHEI is like giving electrons an energy burst to jump the barrier and get trapped.
That's a good way to think about it.
Now, with all this charge moving and being stored long-term, reliability must be a huge concern. What are the key reliability issues?
Absolutely paramount. Two big ones are data retention and disturb effects.
Data retention is just holding the charge.
Exactly. The ability of the floating gate to hold its charge over time. Any leakage means data loss. So the insulator quality is crucial.
How is that tested?
Often using high-temperature tests to accelerate leakage and estimate long-term reliability under normal conditions.
Okay, and disturb effects. Sounds ominous.
They occur when operating on one cell unintentionally affects the state, the data of neighboring cells.
Ow.
Two main types. Program disturb, where programming one cell slightly alters a neighbor, and erase disturb, where erasing a block affects nearby blocks.
Why is flash susceptible?
The drive for high density often means omitting certain select transistors that could help isolate cells, saving space. This can make flash more susceptible than, say, EEPROM.
So you need charge to stay put, and writing erasing shouldn't mess with neighbor.
That's the challenge, yes.
Now, scaling, making cells smaller. Are there unique challenges for flash compared to other chips?
Yes, definitely unique constraints. While the industry trend is always smaller features, flash has tricky voltage requirements.
The low read voltage versus high program erase voltage.
Exactly. During reads, voltages must be low to avoid disturbing the stored charge. But program arrays need significantly higher voltages to move electrons.
So you can't just shrink everything uniformly.
Not easily. Scaling involves reducing feature size, but also carefully thinning insulating films and using clever circuit architecture to maintain performance and reliability as dimensions shrink. It's a careful balancing act.
Sounds tricky. Now, we've talked about flash generically, but the source mentions different types: stacked gate, NAND, DINOR, P-channel. Briefly, what distinguishes them?
They represent variations in the cell's physical structure and the specific program arrays mechanisms used. Each is optimized for different characteristics or applications.
Okay, stacked gate.
A very common. Control gate, physically stacked on the floating gate.
NAND.
We covered that prioritizes density, dominant for mass storage like SSDs, memory cards,
DINOR.
divided bit line and NOR. Aims for low power, fast random access, often used for code execution, especially in mobile.
And P-channel.
Uses P-type transistors instead of the usual N-type. Can offer advantages in specific apps, maybe power consumption in some cases.
And embedded flash.
Crucial category. Flash integrated onto the same chip as other logic like microcontrollers, system-on-a-chip devices.
Yeah.
Very common now.
So it's a whole family of flash technologies, each with strengths and uses.
Exactly. The guide delves into each one in later chapters.
Okay. Now, as we push scaling limits, even the materials come under scrutiny. Emerging tunnel dielectrics instead of silicon dioxide.
Precisely. Silicon dioxide, SiO2, has been the workhorse insulator for ages. But as cells shrink to nanometer scale, SiO2 faces fundamental limits in electrical properties and charge retention.
So researchers are looking at alternatives.
Actively. Materials like silicon nitride, Si3 and 4, and other high-K dielectrics, K refers to the dielectric constant like hafnium dioxide, HFO2, titanium dioxide, TiO2.
What's the advantage of high K?
They offer different electrical properties. A higher dielectric constant could allow using physically thicker films that have the same electrical thickness, EOT, as thinner SiO2.
Thicker films might be more robust, better reliability.
Potentially, yes. Could improve performance and, crucially, long-term reliability and charge retention. Silicon nitride, for example, has different energy barrier heights for electrons and holes compared to SiO2.
Which could be exploited.
Strategically, yes, to get more efficient program arrays while still ensuring good charge confinement for retention. Material science is critical here.
So material science is key to pushing limits, and silicon nitride seems particularly promising.
The source highlights potential advantages. For NOR, maybe higher CHEI efficiency for faster programming.
And for NAND,
Theoretical work suggests potentially higher FN tunneling efficiency for programming and maybe longer data retention compared to SiO2 at the same EOT. It's a very active research area.
and it's not just replacing the whole layer, it advanced barrier engineering. What's that?
Right. Instead of just one material, engineers explore sophisticated layered structures for the tunnel barrier.
Layers of different materials.
Ultra-thin layers of different dielectrics, each with specific energy barrier heights. The goal is to engineer the overall energy profile.
To optimize what?
Optimize tunneling current for program arrays, while minimizing unwanted leakage current that hurts data retention.
Can you give an example?
A crested barrier might have a thin, low barrier material sandwiched between higher barrier materials. Could allow efficient tunneling at lower voltages while still confining charge well in the off state.
Like designing a custom atomic level doorway for electrons.
That's a fantastic way to put it, precisely controlling the electron flow.
Now, all this high voltage and electron movement must stress the materials over time. Reliability issues from operational stress.
Yes, a significant concern is tunnel erase-induced oxide degradation. Repeated erase cycles cause gradual damage to the tunnel oxide.
Creating defects.
Defects or traps within the oxide. These traps affect electrical characteristics, increase charge leakage, reduce data retention.
Anything else.
Under certain conditions, high fields at the drain junction can cause drain avalanche hot carrier, DAHC injection. Hot holes get injected into the oxide, causing further degradation.
So the very act of using it wears it out slowly.
That's the nature of endurance limitations in flash, yes.
So how do manufacturers ensure it still lasts reasonably long, endures enough cycles?
Through extensive, rigorous reliability testing. A crucial test is data retention bake testing at high temperatures.
Baking the chips.
Essentially, yes. For plastic packages, maybe 150 degrees C. For hermetic, maybe 250 degrees C. High temps accelerate charge leakage.
Simulating years of use quickly.
Exactly. Allows estimating long-term retention under normal conditions. The Arrhenius equation is key here.
The one relating reaction rates and temperature.
Yes. It helps analyze charge loss at high temps to determine activation energy of failure mechanisms and extrapolate performance at real-world temps.
And this is done after cycling the chips.
often performed after devices undergo specified program erase cycles to simulate lifetime wear. It's like an accelerated aging process in a hot oven.
Okay, makes sense. Now, we touched on MLC earlier, storing multiple bits per cell for cost reduction. That was huge, right?
Absolutely. MLC, storing 2 or more bits per cell, was a massive breakthrough for reducing cost per bit.
Intel's StrataFlash was an example.
The source highlights it, yes. By doubling capacity in the same silicon area compared to SLC, MLC dramatically lowered manufacturing costs, making flash much more affordable and widespread.
But going from 1 bit to multiple bits per cell must have been tough engineering-wise. Key challenges.
Oh, it definitely increased complexity hugely. The initial vision actually involved needing very sophisticated ECC and highly precise external power supply control.
Oh, they overcame that.
Yes, through advancements in device physics understanding, innovative circuit design, and manufacturing improvements, engineers made MLC more practical.
What were the key enablers?
Accurate charge placement, controlling precisely how much charge goes onto the floating gate. Precise sensing, reliably measuring the stored charge level. And stable data retention, ensuring the charge stays put.
How were those achieved?
Refinements in device operation and the direct cell access of ETX flash architecture help provide better control and reduce interference.
And the result for the user?
Remarkably, end-user functionality of MLC flash is largely indistinguishable from SLC. Comparable read speeds, lower voltages, advanced features like read-while-write, they made immense internal complexity seamless externally.
Very impressive. Now, the outline mentions an alternative, NROM. How's that different from floating gate flash?
Nitride read-only memory, NROM, is a fundamentally different approach. Instead of storing charge on a polysilicon floating gate,
it
stores charge within a thin silicon nitride layer, typically in an nitride-oxide ONO stack.
What are the advantages?
Because charge is trapped locally in the nitride, it can be inherently less susceptible to problems from point defects in the tunnel oxide. Also, potential advantages for scaling down further.
Interesting. Can it do multi-bit?
Yes. NROM can store 2 or even 4 bits per cell by trapping charge in different localized regions along the transistor channel.
Based on nitride's properties.
Exactly. Relies on nitride charge trapping. Might offer simpler scaling rules compared to the precise multiple voltage levels needed in MLC floating gate flash.
So, using nitride instead of a floating gate opens up different possibilities.
Potentially advantageous ones, yes.
Finally, looking beyond flash and NROM, what other emerging non-volatile memory techs are out there? What's next?
The quest continues. A very active research area. Several promising alternatives are being explored.
Such as?
Ferroelectric RAM, FRAM, uses material polarization. Magnetic RAM, MRAM, uses magnetic resistance in magnetic tunnel junctions.
Okay.
Resistive RAM, ReRAM or RAM, changes the resistance of special materials. Phase change memory, PCM, changes the physical phase of a chalcogenide material between amorphous and crystalline states.
Different resistances again.
Right. There's also longer-term research into things like single-electron memories, but they face big challenges currently.
So each has pros and cons.
Each has unique potential advantages and disadvantages regarding speed, power, density, endurance, scalability. It's a very dynamic field.
Lots of possibilities for the future of storage. Okay, as we wrap up this deep dive, what are the key takeaways listeners should remember?
I think the big ones are: flash was born from a specific market need, a quest for better non-volatile storage.
The Holy Grail.
Right. The core principle is trapping charge on an insulated floating gate. NOR and NAND reflect a fundamental speed versus density cost trade-off.
NOR for code, NAND for data.
Generally, yes.
Yeah.
MLC was a huge breakthrough for density, but added complexity and the need for ECC.
Right.
Reliability and scaling remain ongoing critical challenges, driving material science and design innovation.
And flash isn't the end game.
Definitely not. It's important to recognize other advanced non-volatile technologies are on the horizon, potentially offering future improvements.
And maybe the biggest aha moment for me is just realizing the incredible journey behind storing a photo on your phone. From that initial quest in the 80s to today's intricate tech, it's truly remarkable.
Indeed. It really underscores the amazing ingenuity in material science and electrical engineering that underpins so much of our digital world, often silently.
So here's a final food for thought for you, our listener. Considering the seemingly insatiable demand for data storage everywhere,
From wearables to data centers.
what do you think will be the next major breakthrough in non-volatile memory? What limitations of current flash will it absolutely need to overcome?
And what role will material science, electrical engineering, and market demands play in shaping that future?
Something to ponder until our next deep dive. Thanks so much for joining us.